Hello again and welcome. Today we're going to be exploring different visual methods of conducting the arithmetic that we've all been familiar with since grade school, but now we're going to find a way to look at it in a slightly different light. Let's jump right in. The naturals are the easiest of the numbers. They're given their name because they are nature's counting numbers. They're 1, 2, 3, etc. If you want to run an experiment as to why they're called nature's counting numbers, and if you have a pet, then I recommend you try this. Go and get 3 treats out of your pet's treat jar and only give them 2, and see if they know that there's still 1 left over. So these are the simple numbers, the counting numbers, the ones that we all grew up with, learning how to relate via our fingers and counting with objects. To represent them, we can imagine a sandbox that is completely level, and we'll call this sandbox 0. Now if we draw 1 pile in that sandbox, we could use that as a model for the number 1. And similarly for 2, that could be a sandbox with 2 piles. And in this way, we can conduct our basic addition. We can say that 2 plus 3 is really a sandbox that has 2 piles and 3 more piles, so that a small change in our perspective is going to make us look at this as either 2 and 3 piles, or we could look at this as 5 total piles. In fact, we can look at these through a number of different lenses as well. We could say that this is going to be the exact same thing as if I have 1 pile and 4 piles, or 4 piles and 1 pile, because we're just changing our perspective, we're not changing the meaning. We can also do some basic subtraction, like 3 minus 2 can be thought of as 3 piles where we're going to take 2 of them away. So 3 piles where we identify 2 to take away, perhaps these last ones, is going to leave us with 1 pile. And in that way, we see that 3 minus 2 is equal to 1. It's with the help of this model that we can view one of the most principal laws of addition, which we call the commutative law. The commutative law gets its name from the fact that commutative comes from commute, which is to move. So this is the movement law of addition, and it works like this. It says that 3 plus 2 has to equal 2 plus 3. And in fact, if we want to remove ourselves from the specifics of 3 and 2, we can just simply say that a plus b is equal to b plus a. So we can say that 3 plus 2 was that 3 piles and 2 piles, which of course we can look at as being 3 and 2, or we can look at it as being 2 and 3, and in the same way, a plus b we can just write as being 1 pile, 2 piles. Well, I'm not entirely sure how many a is if we're going to keep it abstract, so maybe I'll just put some dots in between, and I'll say this is a number of piles. And of course that's going to get us the same total if we combine it with b total piles, as we would have gotten if we just simply did b first and then added those a piles to it as well. Recall that the integers get their name from the same root as the word integral or integrity, meaning complete. So these are our complete positive and negative numbers. Our -2, -1, 0, 1, 2, they're the positive and negative whole numbers. So we can look at expanding our model of piles to now be a model that has both piles and wholes. So for example, let's do 3 plus -2. Well, we can draw that by using 3 piles, 1, 2, 3, and then we can just add onto it 2 things that are the opposite of piles. We're going to add the opposite of 2 piles. Well, what would the opposite of 2 piles be? 2 wholes. So we'll put 2 wholes in our sandbox. Now we can look at this sandbox as having the equivalent amount of sand, the same amount of sand, as a sandbox that had only 1 pile. And we can see that because we can look at how these piles would have respectively filled each of these holes. So we now know that 3 plus -2 is going to be equal to 1. And in fact, we now know as well that we could look at this in the same light as 3 minus 2, because what we get whenever we are combining addition and negatives is that we get a cancellation that can occur that's the same thing as taking some away. Now that we know how to represent our work using the piles and holes model, we can introduce another model, one of blocks and anti-blocks. It's the exact same thing, but instead of using piles and holes, if we want to represent 3 plus negative 2, we can choose to do that by having 3 blocks and combining that with 2 anti-blocks. Maybe I'll shade these in to show that they are the opposite of the unshaded regular blocks. So these each represent a -1, and these each represent a +1. If you'd like, you can imagine that these blocks are what the piles look like if you look at them from above. So the non-filled blocks are nothing more than square-shaped piles that you are looking down on. Meanwhile, the shaded blocks are square-shaped holes that we're looking down on. Well, they're going to behave in the same way as the piles and holes, in that a positive block and an anti-block will be able to annihilate each other, leaving us just with an equivalent 1 block, which is the same amount as we would get if we had done 3 minus 2, because in that elimination, it's the same thing as if we had taken away. Let's move on from addition and subtraction to multiplication. Let's see why it is that 3 times 2 is the same thing as 2 times 3. Well, this is in fact a story. 3 times 2 is 3 times of 2. So if we want to do 3 times of 2, we can think of that as first starting with 2 blocks, and then we will repeat this picture 3 times. So we will have a second repetition, and then a third repetition. So we have 3 times of 2. Now, is it true that that's the same as 2 times of 3? Well, obviously that's going to be 6, but let's use our visual model to show why one instance of 3 and then a second instance of 3 has to be the same as 3 instances of 2. And it's in representing these visually that we see that it does not matter if we do multiplication of one term before the other or the other before the first, we're going to produce the exact same collection, and all we have changed is how we flip our perspective. So it's through this diagram that we can see that we have a commutative law for multiplication as well. A times B is the same thing as B times A, where that word commutative reminds us that all this is the ability to move things throughout that operation. And this has to be true, because if we have A times of B, we can always represent this as a rectangle, where in that first row, we have B instances of these blocks. I don't know exactly how much B is, because we're keeping it general, so I'll just put some blocks and a dot, dot, dot to show that there are some more. But A times of that means that we're going to repeat this entire collection of B multiple times. How many times? Well, A times. So we will always be producing a rectangle that has A instances of B, and through that rectangle, if we flip our perspective, we will be able to view this as instead B instances of A. So what about multiplication by negatives? Let's look at an example of 3 times -2. Well, with our aid of the visual model, we can view this as 3 times of these -2's. And we know how to represent -2's using our anti-blocks. So we can say that that is one anti-block and another anti-block, each representing -1. So together this is -2. And 3 of those -2's would be 3 repetitions of those 2 anti-blocks. Meaning that now we don't have -2, but we have -6. We have 6 anti-blocks because it's what has to result from 3 groupings of -2. And we can see that this still works via our commutative law, because if I want to look at -2 times 3, this would be read as the opposite. Remember that we said negatives are opposites, so this is the opposite of two groups of 3. Well, two groups of 3 would be 1, 2, 3 for one group, 1, 2, 3 for a second group, and so this would be two groups of 3. Well, the opposite of two groups of 3 would be that if these are all positive blocks, or we can think of them as piles viewed from above, then the opposite of that would be turning them into wholes or anti-blocks. So we'll just fill them all in. That gets us negative 2 groups of 3, which is the same thing as 3 groups of negative 2. Lastly, I'd like to show you 2 different models that help make intuitive sense out of the operation of division. The first is dot division. So let's look at this problem, 36 divided by 3. If we want to do 36 divided by 3, we could think of that as 36 divided into groups of 3. So this is an operation of grouping. It's the opposite of multiplication, which created repetitions. Here, we're going to be taking 3's and grouping them together in one group. So let's look at 36 dots and sketch those out real quick. These are 36 dots, and if we want to group them into 3's, all we need to do is search around for 3 and then form a group around them. So we can do this working our way through the entire collection. In doing so, I'm able to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total groups. And this is why 36 divided into groups of 3 creates 12 total groups. Now this can be cumbersome when we're dealing with large numbers of dots, so one way to help make this faster is that we can look at dot division where we use dots in combination with their place values. So for example, we could put 3 dots in one box and identify this box as being tens. So each of these represents 10 in quantity. And similarly, we can create a ones place where we would put in 6 different dots. So these would be 30 and 6 dots. When we're creating groups, we still can group by those 3's. So we get one group of 3 in the tens place, and we get 2 groups of 3 in the ones place. And this allows us to identify that I have one group of tens and 2 groups of ones, making 12 total groups altogether. It's from this diagram that we get another model, the area model, one of my favorites to use for large amounts of division or representing difficult problems. In this area model, we just have to imagine that we have a rectangle where the inside area is 36. Now this makes sense because area is equal to length times width when you're dealing with a rectangle. We saw that when we did 2 times 3 and how it produced 6 total blocks on the inside of our rectangle. Well, similarly then, that means that the area, if I have identified one of the lengths, can be divided by it to produce the width. So the area can be thought of as the 36, and one of the sides can be identified as 3. And all we are trying to do is find the other. Now we can work through this in a couple of different ways. One of my favorites is to represent this rectangle where you have the tens place and the ones place. So where 3 is on the outside and 36 is on the inside, we're going to write 30 and 6 instead of 36. And that helps us see that we have 10 by 3 creates a 30 area, and 2 by 3 creates a 6 area, so we have 10 and 2 for our length. Many of us are probably familiar with the traditional method of doing division, which is to do long division. But this is a procedure that is only comfortable for us because we've practiced it a lot, not because it makes a lot of intuitive sense. For example, let's do 1,244 divided by 4. Now we have to remember that if we're going to do long division, we've got to draw an entirely new symbol. And instead of reading this from left to right, we are now going to write this from right to left. Once we have this set up, then we need to ask ourselves not how does 4 go into 1,244, but how does it only go into the first digit, the 1, which it doesn't. So we might put a 0 on top and say that 0 times 4 is 0, and that we do subtraction not of the full number, but just of the zeros place, but just of the thousandths place to produce 1. Then we do something we don't do in any other form of mathematics. We consider just a next place value and carry it down to create an entirely different number that we then repeat the procedure with. To see why this method works, let's do the dot division alongside it. So we'll put 1,244 into a place value system using the dots the same way that we did in the previous examples. 1, 2, 4, and 4. Now if we wanted to do dot division and find groups of 4, we might start with any of the boxes. But to match the traditional algorithm, let's start with the leftmost box and recognize that because there's only one dot in it, this dot needs to be exchanged for 10 more dots in the hundreds place. Once we've removed this dot and exchanged it for 10 hundreds, we can go about finding those groups of 4. A group of 4 here, a group of 4 here, and a group of 4 here, creating 3 total groups of 4. If we return to our traditional algorithm, we can see that that's exactly what we did with these symbols. We started with just the 1 in the very beginning and saw that there were no 4s that could be grouped out of that 1. So instead, we needed to turn the 1 into 10 hundreds to partner with the 2 hundreds, and then we could consider those 12 dots as their own set, producing 3 groups of 4, which accounted for 12 of the dots and removed them from needing to have a group. Then we would move on to the next part of our diagram, where there are 4 dots awaiting us in the tens place, and we can group them all. This was always a very confusing topic for me because there was nothing else in mathematics I wasn't able to explore. Why was it that it seemed that teachers and calculators were all in a conspiracy to keep me from dividing by 0? Whenever I asked people, the rules that I often got were also very bad metaphors. Something along the lines of, well, go try to distribute 4 amongst 0 people, or go try and do division by 0. I never liked these explanations either because I had never physically gone and divided 5 amongst -5 or any of these other abstract ideas. So instead of giving a rule, let's use our models to understand what's actually occurring when we divide by 0. So we'll start off with looking at the area model. The area model, whenever we're dividing by 0, let's take for example 5 divided by 0, tells us that we have a rectangle whose area is size 5, and one of the side lengths is 0. And we're simply trying to figure out what the other side is. Well, this visual model now makes it incredibly obvious why we're going to have difficulty determining what that question mark is. Because anything that has 0 height does not have a height. And so it's impossible to have an area of 5 if really what this diagram is describing is something with no height, something that is flat, with a 0 area. So how can we find another number that works for the question mark and holds true for this entire model? The truth is that we can't, that this right here does not exist. There is not a single number that if we multiply it by 0 will produce an area of size 5. So this is why we're not able to divide by 0, not because we're prevented from doing so, just because there is not a number that will actually make this true. Now, as a fun little comparison, we might ask, what is 0 divided by 0? Now, we know that this is going to be an answer that we can't determine because dividing by 0 is not something that... Now, in this situation, we get an error, but not one that's the same as but not one that's the same as what happened in the previous picture. Here, 0 divided by 0 would be a zero-sized area, where one of the side lengths is also 0, and we're being asked to figure out the other. Well, 0 as a height would in fact produce a 0 area, because it would flatten this structure until there was no space on the inside. But what is the other side length that makes this possible? In truth, this could be anything, because anything times a height of 0 would not be enough to make the inside anything but a 0 area. Well, if it can be anything, and we're being asked to pin down a specific number, then we will say instead that this is undefined. So undefined does not mean that it can't work. In fact, it just means that it works for too many possible answers, so it's impossible for us to pin down the correct one. Because recognizing what numbers different numbers are divisible by is challenging, I'd like to close on a couple of shortcuts that will help you recognize when numbers are divisible by 2, 3, and 5 without remainder. So let's start with this statement. A number a is divisible by 2 if and only if the ones digit of a is a 2, a 4, 6, 8, or 0. In other words, if a is even, then we should be able to divide it by 2. To see why this works, we might start with the dot diagram and use an example of a number that we know is divisible by 2, but that is much larger than the numbers we usually experience, like 242. We know that is going to be divisible by 2 because if we draw the dot diagram, we'll be putting 2 dots in each of the categories, except for the tens place, which will get 4 dots. But since every stage has the ability to be grouped into 2's, this must be divisible by 2. Now, if we want to look at a number that is maybe not as obvious, but still able to be divided by 2, we might choose something like 32. Now, 32 violates the shortcut that we were just talking about, because we will have 3 dots in the tens place and 2 dots in the ones place. So when we go about making our groups, we will not be able to use up all the tens in one group. But that remaining dot can always be exchanged for 10 ones dots. And once we put 10 ones dots in our diagram, we know we will be able to create groups of 2, because 10 is 2 groups of 5. In other words, even if we have a dot that is in the hundreds place, the hundreds place dot, we will be able to take that dot and exchange it for groups of 10. And even if we don't recognize that the 10 groups of 10 can be grouped already, and instead we exchange each of those 10 dots for 10 ones, we will still be creating groups of 10 in the ones place. So it does not matter what's in the hundreds place or the tens place. If we can group whatever we want in the ones place, then the 100s and the tens must be even as a natural result of them having 5 groups of 2 hidden many times over within them. To find out if a number is divisible by 3, we only need to consider each of the digits in the number and what they add to. So for example, let's start with 372. Now, this number is not easy to determine whether or not it is divisible by 3. If we use our dot diagram, we have 2 dots left over in the ones place, we have 7 dots in the tens place, and 3 dots in the hundreds place. Now we can go through the effort of grouping and moving our remainders, but we would like to verify this statement, that this is divisible by 3 only because 3 plus 7 plus 2 produces 12, and 12 is divisible by 3 because 1 plus 2 is 3, and 3 we know is divisible by 3. This is a very weird cadence, a weird shortcut. So let's look at it from the other direction. Let's begin with a dot diagram that represents 3. We'll create our diagram with our ones, tens, and hundreds place, and only put 3 dots on the inside. So far, we can agree that 3 dots in the ones place gives us just the digit of 3, which is something that we know is divisible by 3, so all looks good. We can in fact go up from that to 6 and 9, and we will recognize that we will have still something that follows our shortcut. This would be 3, this would be 6, and then we could make it with 9 as well. But I'd like to then take a look at what happens when we get to 12, our first number that is 2 digits and divisible by 3. If we introduce 3 more dots into this ones place, then we will have enough that we can exchange 10 of them for a tens dot. In doing so, we can recognize that what happened with that last group of 3 that we added is that we used 1 to complete the tens that is now represented as a single dot in the second column. If we do this again and we do it for 15 and then 18, then all we have created is 3's in the ones place that complement the fact that we already have 3 dots in the 3 that we got from the 12. If we add one last group of 3 dots in the ones place, now we will be using all of the dots that we had created and 1 from what remained after our first grouping to create a second dot in the tens place. And now we can see that the digits still add up to something that is divisible by 3. 2 and 1 creates 3 visual dots that help us recognize that we have created a number by only adding groups of 3. And if we do this cycle one more time where we add 9 more dots to the ones place, then we'll be able to use up all of the remainders that were in the ones place from our initial grouping, and that will have created 3 dots in the tens place and no dots in the ones place if we grow this pattern all the way up to 30. And once we get to 30, we are just repeating the same pattern again and again, where we are able to add up to 9 dots in the ones place, because on the 12th dot addition, we will be able to form a group that leaves 2 behind, creates a single dot in the next place value, and begins this entire cycle over again, where we always have a complement of the number of dots in each category adding up to 3. Lastly, let's look at how we can recognize if a number is divisible by 5. Here we have it stated that a number 5, if and only if it has a 0 or a 5 in the ones place. To see that, let's again use our dot diagram. So we'll start off with an empty diagram with a ones, tens, and hundreds place. And then we will consider if we put nothing in the diagram, then we can find no groups of 5. If we put 5 in the diagram, then we can find one group of 5. If we put another 5 dots in this diagram, then we'll be able to create one whole group that creates a dot in the tens place. All of those together. And just like with our exploration of 3's, once this pattern repeats, we can expect it to repeat every time. So if we then add another 5 dots, then we still have 5 that is in the final column, and if we add another 5, we'll be able to group that into a dot in the tens place. And this gives us our last little bit of insight, which is that, of course, the 100s dots and the tens dots will always be divisible by 5, because 10 is divisible by 5, and 100 is just a bunch of tens. The only thing that could get in the way of our ability to make groups would be how many dots there are in the ones place. So there you have it. Arithmetic using all of the numbers included in the integers. That's all of your addition, subtraction, multiplication, and division, where you can represent all of these procedures using models that make intuitive sense to you and are able to be expanded for as large a number as you want to consider.